Electric Potential Conductors, Lesson 3.5. Our learning objectives will be to identify the properties of conductors in electrostatic equilibrium, characterize the electric fields of conducting materials, and to calculate the electric potential on and inside conductors. Introduction. In 1836, the great British scientist Michael Faraday conducted experiments that led to the invention of the famed Faraday's cage, a variation of which is shown in the photo above. This room, or cage, was completely wrapped in metal foil and permitted discharges of high voltage from an electrostatic generator activated outside the room. Faraday then used an electroscope, an instrument used to measure electricity, to prove that no excess charge entered the cage's walls and volume. This phenomenon is called the electrostatic equilibrium of conductors. Let us further explore its relationship with the electric field and potential in the lesson that follows. A conductor permits free electrons, also called conduction electrons, to freely move between and among atoms. Every time a conductor receives an excess charge, it scatters about the conducting material such that the totality of repulsive forces inside the conductor will be reduced. This is referred to as electrostatic equilibrium. As soon as a charge-conducting material reaches electrostatic equilibrium, charges can no longer move about the surface. The first characteristic of conducting materials at electrostatic equilibrium is that the field and the conductor's surface are directed perpendicular to each other. Hence, if the conductor is spherical, the perpendicular field vectors are aligned with the sphere's center. If it is, however, shaped irregularly, then the field vector will be perpendicular to any tangential to the surface. Figure 3.5.2, Perpendicularity of electric field and conductor's surface. Figure 3.5.2 illustrates how free charges are affected by an electric field inside a conducting material. Since the field is a vector with parallel and perpendicular components, the parallel component exerts a parallel force on the point charge, hence cancelling out. The free charges are then distributed until the electric field and the surface are perpendicular. Figure 3.5.3, Polarization of a conductor by an external charge Q. Another important thing to note is that under electrostatic equilibrium, the charges are distributed such that no electric field is present inside the conducting material. Consider, for instance, a conductor close to a positive charge. The metal's conduction electrons are attracted to the external positively charged particle and freely move toward that region. This region, to which these free electrons move now, has more electrons than protons inside the atoms, whereas the region from where the electrons displaced contains more protons than electrons. This results in a negative region close to the charge and a positive region on the other end. As shown in figure 3.5.3, this separation between the equal and opposite electric charge is referred to as polarization. Recall that Gauss's law that in the electric field of a charged sphere, the field outside the sphere is similar to that of a single charged particle. Hence, the electric potential will also be the same and is given by equation 3.5.1. It has been established that the electric field within a conducting sphere is equivalent to zero. This concludes that the electric potential will remain constant at the value that it has reached on the conductor's surface. Thus, the potential difference or voltage inside a conducting material in electrostatic equilibrium will also remain at this constant value. Considering that the electric field is equivalent to the rate of change of the electric potential, figure 3.5.4 shows the relationship between and among these variables.
Now let's move on to let's practice. We have example number 1. A conducting hollow ball with a radius of 0.5 meter has a charge with magnitude 4.3 UC. What is the electric potential at the surface of the conductor? The solution is identify what is required in the problem. You're asked to calculate the electric potential at the surface of the conductor. Step 2 would be identify the given in the problem. The magnitude of the charge, 4.2 UC, and the radius of the conducting ball, 0.5 meters, are given. The value of K, or Coulomb's constant, is 9.9 times 10 to the power of 9 nm squared divided by c squared. Step 3, express the equation to be used. So, muna equation. Ang V, kay muna siya ang electric potential. Ang K is ang Coulomb's constant. Ang Q kay ang electric charge. Then ang R ay radius or distance. And you substitute the given values. And ang 9 times 10 muna siya ang Coulomb's constant. 4.3 ang charge, then ang 3 ay ang R kay 0.5 meters mo na siya ang value, then ang radius. Then you get the answer, which is V surface is equal to 7.74 times 10 to the power of 4 volts. Example number 2. Consider the spherical conductor in the figure below. The conductor material shown above has a radius of 3 cm. If the electric potential at point B, which is 2 cm from the center, is equal to 3 times 10 to the power of 5 volts, calculate the magnitude of the charge. So, ato ang kuhaan diri kay ang charge, which is sa bilang atong kuhaan. Now, ang given diri kay ang radius, which is 3 cm for the sphere and 2 cm for point B lang. And ang electric potential diri kay 3 times 10 to the power 5 volts. Pero note na ang kuan, ang electric potential ani na points A and B is dili sila different. Since namoya po sila sulod sa sphere. So pareha ra gyapon. So karon atong kuan lang is ang magnitude of the charge. Solution. Step 1. Identify what is required in the problem. You're asked to calculate the magnitude of the charge. Step 2. Identify the given in the problem. The electric potential at point A, 3 times 10 to the power 5 volts, and the radius 3 cm are given. Note that the electric potential at the surface, point B, will be constrained to the same value at point A. So, pareha ra ang electric potential. Step 3, ato nang i-derive ang formula. So, interchange lang ang mga values. So, instead of V, mahimo ng Q since ang charge man atong pangitaon. Then, instead of Coulomb's constant, mahimo na siyang ang electric potential. Then, mababa ng Coulomb's constant. Then, i-substitute lang nato. And 3 times 10 to the power 5 volts mo na siya ang electric potential. Then, i-times nimo sa radius or distance, that is 0.3 meters, which is distance sa point A. Kaya pareha raman ang ilahang kuan, electric potential sa point A, point B, therefore pareha ra sad ng ilang magnitude. Then i-divide nimo by 9 times 10 to the power of 9, which is ang Coulomb's constant. Then ang answer kay ang Q equals 1.00 times 10 to the power of 6. And C. Yan, mauna na ang answer sa problem 2. Dili na ta sa example number 3, which is consider the spherical conductor below. Then naata diri kuan circle na conductor, then ay 4 ka points, which is A, B, C, and D. Ang distance nila between each other is shown above. So ang distance sa A and B is 12 millimeters. Ang distance sa B and C is 15 millimeters. Then ang distance sa C ug D is 48 millimeters. The hollow metal ball above has an electric charge of 7.83 UC. The distance between points A and B is 12 millimeters. Between B and C is 15 millimeters, and between C and D is 48 millimeters. What are the corresponding electric potentials at point C and D? So, itong pangitawon lang na missing is ang electric potential sa point C and D. Then, ang solution is to first we identify what is required in the problem. We are asked to calculate the electric potentials at point C and D. Step 2 ang given sa problem, which is ang magnitude kay 7.83, and ang distances kay AB kay 12, BC kay 15, and CD kay 48 millimeters. Now, i-calculate sana to ang distance or ang radius para kay C. Para makuha ni kay i-plus na si AB plus BC. Then, ang ilang result kay 27 millimeters or 0.027 meters. Then, i-identify na sad nato ang distance kay D, which is makuha by adding AB plus BC plus CD. I-add na nimo, makuha nimo kay 75 millimeters or 0.075 meters. Then, ang equation na to nang i-derive. So, dili na siya need i-change, kana lang. V is equal to KQR divided by R. Then, substitute na nato. Para kay VC, kay 9 times 10, which is ang koan to the power of 9 to the, ang koan, Coulomb's constant, then i-times na to sa 7.83 times 10 to the power of negative 6, which is ang electric charge. Then, i-divide mo by 27 times 10 to the power of 3. Kaya mo man ang ato ang radius. Then, sa D, kay 9 times 10, which is Coulomb's constant, times 7.83, which is ang electric charge, divided by 75 times 10 to the power of 3, which is ang ato ang distance para kay D. Now, naana diri ang answer, which is 2.61 times 10 to the power of 6 volts kay C, tas D kay 9.40 times 10 to the power of 5 volts. Then, muna na ang 3.